Welcome all to the seventh discussion session of the course Plates and Cells offered by NPTEL. The course instructor of this course is Professor Sudeep Talukdar and I am your teaching assistant. Myself, Asif Raza. I am a PhD scholar from Department of Civil Engineering, ISC Bangalore. So as it's already 3 p.m., so let's start our session. Okay, so the first question is you have to state whether the statement is true or false. The mode shape of free vibration of a beam can be used as trial function in Rayleigh-Ritz approximate methods. So, in Rayleigh-Ritz approximate methods, we take displacement function uh, like we approximate displacement as a1 f1 x comma y plus a2 f2 x comma y, likewise a and fn x comma y. So this fx, these functions can be taken as mod shape of free vibration of a beam. That's the question. So this statement is true. The statement is true. Next question is, there is a rectangular plate with dimension 2a by 2b, has identical boundary condition at all edges. The origin is taken at the center of the plate. Given an approximate deflection function is. So we have to find what kind of boundary condition we have. So we are given with a rectangular plate with x and y as this is equal to a, this is y equal to b minus and y equal to minus b. Okay. So as there is a statement that there is an identical boundary condition at all edges, we'll just take one of the edge and try to find. So at x equal to a, what do we have? If we substitute a comma y, we get a1 by 4 1 plus cos by a by a plus 1 cos pi y by b. So this will give me minus 1 and as a result this will give me 0. So we have the deflection come out to be 0. Now let's find del w by del x. This point is comma y, it will be a1 and 4 minus pi by a sin pi x, or rather write it as pi by a minus sin pi x by a 1 plus cos pi y by b. And if we substitute in the place of x as a, we get therefore pi by a minus sin pi a by a 1 plus cos pi y by b, and this will give me 0. So as a result we have the slope at this point as 0. So at edge x equal to a, we have the deflection and the slope come out to be 0. Using this condition, we'll be having displacement restricted at all the edges and the slope would be also 0. So that would give me what? Fixed condition at all edges. So correct answer would be option B. Now this is third question. We are given with the expression of the strain energy of the plate. Suppose the plate carries uniformly distributed load Q with the aspect ratio of A by V is equal to 1.5, Poisson's ratio is 0.3 and modulus velocity of the material E. Using Rayleigh-Ritz method, deflection at the center of the plate is and we have to find the value of K. So we are given with the value of strain energy, and the displacement function would be used this one, that is W for x comma y is equal to a1 by 4 1 plus cos phi x by a 1 plus cos phi y by b. Right now, see, we have the strain energy density given as to be this. We need to find the deflection at the center, and the approximated displacement has been taken as this. So we need to find, so what would be the work done by the external load? It will be Q W xy dx dy, and our x is from minus a to a and y is from minus b to b. So this would be equal to dx dy. So on integrating this, we'll get cos pi x as sin pi x. So this will give me as a result 2a and 2b, that will be equals to q a11 ab. Okay, now my potential energy function would be equal to u minus w, so that will be equal to d pi 4 a11 square 32 3b by aq plus 3a by bq plus 2ab minus q a11 ab. This is my potential energy function. Now using Rayleigh-Ritz method, use this equal to 0. So this will result into d by 4 a11 by 16 and 3b by aq plus 3a by bq plus 2 upon ab minus qab equal to 0. So on simplifying this, we'll get a11 as 16 qab upon d by 4 3b by aq plus 3a by bq plus 2 ab. Right, so we need to find deflection at the center. So deflection at the center would be W 0 comma 0, that would be a1 1 by 4 1 plus 1 1 plus 1, that is a11. So W at center is W at center is equal to a11, that is 16 QAB d by 4 3b aq plus 3a bq plus 2 upon ab. Now we are given with the condition that a by b is equal to 1.5. A by b is equal to 1.5. Substitute b is equal to a. This will be 2 by 3. Substitute in this equation. So W center will come out to be 16 Q A. This would be 2 by 3A. D by 4 3 2 by 3A AQ plus 3A. This would be 2 by 3 AQ plus 2A and 2 by 3A. Finally simplify it. This would be 16 to 32 by 3 QA square. This is D by 4. This would be 2A upon A square, 2 upon A square. This would be 3 3 is 9, 3 is 27, 81 upon 8 A square plus 2 3 upon A square. So simplifying it will get the value as 2 plus 21 plus 3 into 32 50. So this will give me 0.7052. So 7052 QA4 upon D. Okay, so this is in terms of EHQ. D is EHQ upon 12, 1 minus nu square, and nu is 0.3. So EHQ 12, 1 minus 0.3 square. So this is EHQ 12 is 0.9, 12 into 0.91. So substitute this would be 32 by 3 QA square. EHQ 12 into 0.91 by 4 2A square plus 51 8A square plus 3A square. So 4 into 12 into 0.91 divided by 5 to the power 4. So this will come out to 0.0791 QA to the power 4 upon EHQ, which is equal to 0.079 QA4 EHQ. There's K equals to 0.079. Okay, let's move on to the next question. So We are given with a circular plate of radius r, which is symmetrically loaded, is resting on the elastic subgrade of modulus k. D is the flexural rigidity of the plate. Poisson's ratio is equal to 0.3. The boundary of the plate is free, so that the deflection is approximated with this. Okay, so this is the case. So we are given with the approximation function a plus b r square. You know, the strain energy of the plate is given by the relation phi d 0 to capital R d to r square plus 1 by r d w by d r whole square minus 2 1 minus nu upon r dw by dr d second derivative of this, and this is integrated from dr. So we have w as equal to a plus br square, then dw by dr would be equals to 2br, and second derivative of w with respect to r would be 2b. Substituting this into the equation, we'll get Ps by d 0 to r d square, this will be 2b plus 1 by r, so this would also give me 2b minus 2 1 minus nu upon r dw by dr is 2br, and this is 2b r dr, so rr will cancel out. 0 to r 4b, this would be 4b 16b square minus this would be 2 to the 4 8b square 1 minus nu r dr. That means this would be equal to phi d 16b square 8b square 1 plus nu, and r would be this r square by 2. So up is my pi d 4b square 1 plus nu, that is 0.3 r square. So 1.3 into 4, this would be 5.2 pi d b square r square. So this is my answer. Correct answer would be option C. Now let's move on to the fifth question. We are given with a square plate of side A 850 mm, thickness is 14 mm, material properties as Young's modulus of elasticity as 200 gigapascal, Poisson's ratio is 0.25, and this plate is simply supported along all edges. Displacement function has been given as 0.25 sin pi x upon a sin pi y upon a. The strain energy of the plate, we need to taking the strain, we need to find the strain energy of the plate rated up to 3 decimal seconds. So let's start. We are given with equal to 850 mm, H equal to 14 mm, equal to 2 into 10 to the power 5 Newton square, Newton per mm square. Then Poisson's ratio as 0.25. Given we are given with the W as 0.25 sin pi x upon a sin pi y upon a. So strain energy, we need to find the strain energy of plate. We are given with the condition that the plate is simply supported at all edges, along all edges. So the potential energy of the plate will be given by the relation 0 to A, 0 to A, then del square W by del x square, del square W del y square whole square dx dy. Okay, so now this will be equal to d by 2, 0 to A, 0 to A, del square W by del x square would be equal to minus pi by A whole square 0.25 sin pi x upon A sin pi y upon A. Similarly, del square W by del y square would be equal to minus pi by A whole square times 0.25 sin pi x upon A sin pi y upon A. Substituting this, we'll get pi by A to the power 4 0.25 square sin square x upon A. Sorry. Okay, so this would be like 2 times of this, 2 to the 4, 4 into 0.25 whole square. Let me take this, 2 into pi by A whole square times 0.25 minus sin pi x upon A sin pi y upon A whole square dx dy. This will be equal to d by 2. We can take this 0.25 square outside, then pi by A to the power 4, and this is equal to 4, 0 to A, 0 to A sin pi x by A sin pi y by A dx dy. This would be equal to d by 2.25 square pi by A to the power 4, 4. Integrating this, sin pi x by A 0 to A dx would be cos pi x by A to A. This will give me cos A minus 1. And this is equal to pi cos pi minus 1, this would be equal to 1 minus, if I take this minus as outside, then this would be minus 1 minus cos 0, that is 1. So this would be 2a upon pi. So this will come out to be 2a upon pi, 2a upon pi. Got it. Okay, this would be sin square pi x, sin square pi y. Okay, so sin square pi x by a 0 to a is equal to 1 minus cos square x, and that will be this will give me a by 2. So a by 2 times a by 2. So my strain energy of the plate is negative 4 d by 2 times 0.25 square into pi by a 4 if I cancel out a square. D is EHQ upon 12 1 minus mu square. EHQ 12 2 is 24 1 minus mu square. This is 1 by 4. This gives me 1 by 16. Pi by 4 a square. Sorry. Pi by 4 a square. Substitute the values. So this is 2 into 10 to the power 5. H is 14. Q pi 4 24 1 minus mu a 0.25 square 16. This is 850. So the value will come out to be 14 cube into pi to the power 4 into 2 divided by 24. So this comes out to be 2.05529 into 10 to the power 2 Newton mm. So 10 to the power, this will give me 0.2055 Newton meter. Round, you have to round off to 3 decimal place. The UPI will come up to 0.206 Newton meter. So this is my answer. Now next question. As there is a square plate which is simply supported along the edges. The size of the plate is 2a by 2. The thickness of the plate is h. Metal properties are E and nu. E and nu are the modulus of elasticity and Poisson's ratio respectively. To find out the deflection of the plate using finite difference method, the plate is divided into 2 by t equal pieces. Poisson's ratio value is 0.3. The deflection at the center of the plate is given by this, where lambda is constant. We need to find the value of lambda. So let's draw what we are given first. We are given with a square plate. Okay. Simply supported along all edges. We need to divide into 2 by 2 measures. So okay. To find the deflection of the center, let me take this as 1, this as 2, taking symmetry into consideration, this will be 2, this as 3, 3, 3, 3. We'll extend this to the imaginary point 4, 4. Okay. Now we know the mx is given by this using finite difference method. Mx is given by this. So mx at 1. It's okay. So we have simply supported boundary condition along the all edges, so that will give me displacement values at w3 w2 equal to 0. Okay, as it is simply supported. We have mx at the point 2. If we see mx value at 2, what do we have as minus d by h square. See, so we will get the value when we use this and keep this at the point 2. Suppose this 2, so this value and this value is 0, and this is also 0, so we get the value of 1 and 4. 1 and 4 will get by this, that is minus d by h square, that will be equal to w4, and that is 0, and w1 equal to 0. So this gives me w4 is equal to minus w1. Okay. Now we need to find the deflection at the center of the plate. So using plate equation at not 1, we'll get, we have the plate equation to be this, so we keep the node 1 there. So likewise we will be having this 4 here, 4, 4. Okay, so when we keep that here, let's do this the next page. So we have the node 1 here, 2, 2, 2, 2, these are 3, and these are 4. So a value will come out to be, so how many 4? 4 into w4 plus 4 into w4, w3 is 4 into 2w3 plus 4 into minus 8W2 plus 20W1 into 20W1 is equal to Q. We have FQ QH4 by D, right? In our context, so this H would be value of a to the power 4D. Let's now simplify this. So we have W2 to be 0, okay, W3 to be 0, and W4 is equal to minus W1. So this is minus 4W1 plus 20W1 QA4 by D. So 16W1 QA4 by D, W1 is equal to QA4 upon 16D. What terms we have to find? Okay, so I need to simplify much more. We have QA4 16, D is EHQ upon 12, 1 minus nu is 0.3 square. Simplify it, we'll get 16 to minus 0.3. This is equal to 0.6825 QA4 EHQ W1. So this is my answer. Thus lambda value will come out to 0.6825. Okay. Now the seventh question, we have a common data for question 7 and 8. A square plate is simply supported along the edges. The deflection values under uniformly distributed load Q at the nodes 1, 2, 3 are W1, W2 as 5, 3, and 2 mm respectively. The plate is divided into 4 by 4 message division. H in the figure is 0.3 meter. Given E equal to 210 GP and Poisson's ratio is 0.3, the thickness of the plate is A. So we need to find the bending moment Mx at the center, that is node at 1. So we have Mx as this. We'll put this at node 1. So first let's just find the value of D. So we are given with, so D would be E. Okay, so let's use thickness. So we are given with the values thickness as 8 mm, E as 210 GPa, that means 2.1 into 10 to the power 5 Newton per mm square. Poisson's ratio is 0.3. So we can take your 12 minus 1 square as 0.3 square. This would be equal to 9.846 into 10 power 6 Newton mm. Okay, now we need to find the bending moment mx at the center. Using finite difference method, we have this. So when we find this at node 1, we'll get minus d upon h square equals to, so this would be w2, w2, this would be 1, this would be 2 and 2, right? Yeah. So we have 4 into, okay, so minus 2 mu times w1 plus 2 into w2 plus 2 into mu times w2 equals to, substitute the values. This is minus 9.846 into 10 power 6. H is 0.3 meters, 0.3 meter into 10 power 3 square, and minus 2 mu is 0.3 mu, okay, mu is what, mu 0.3. w1 is 5, 2, w2 is 3, 2 into 0.3, and w2 is 0.3, sorry, 3. So this would give me, this one, okay, this would be equal to minus 0.6 minus 2.6 into 5 plus 6 plus 1.8, so 7.8 minus 2.6 into 5 into 9.846 divided by 0.3. This is equal to 568.88 Newton per m. So this is my answer. And due to symmetry, this will be also equal to this. Now for the last question of the session, we need to find the magnitude of the twisting moment at node 3 in Newton per mm. So at node 3, so this is the one. So we know for mxy is this. So for mxy we have minus 2 1 minus nu upon 4h square. This is 1 0 minus 1 0 minus 1 0. So when we keep this at node 3, we'll get 1.4 square as node 3. When we keep at node 3, so this is 2 This is 2, this will be 0, 0, and this is 2. So these values are 0, 0, 0, 0, and this would be 2. So value will come out to be W2 white. Check again. Okay, so this is 1. Is that 2? 2, 2. This would be 1. So final value will come out to be minus 9.846 into 10 power 6. Take it, yeah. 1 minus 0.3. So H is, so in this H is 0.3 meter. So 0.3 into 10.3 square xy. xy okay. Minus 1. So this will, we have the value of W1 as 5, and the value will come out to be 9.846 and 2.7 into 5 24 divided by 95.725 Newton mm per mm. Thus mxy is equal to minus 95.7273 Newton mm per mm. Okay, so when we take the magnitude, it's equal to 95.73 mm per mm. So this is the answer. That's all for today's session. If you guys have any doubt, please post it in the group. Okay, thank you.